Welcome to the lecture titled Improved Identification Using Fourier Series and Wavelet Transform. When the limit cycle parameters are obtained accurately, then the transfer function model parameters can be estimated accurately. So, it is very essential to have accuracy of the measurements, or it is essential to make measurements accurately, so that the transfer function model parameters can be estimated accurately. In today's lecture, we shall see how one can make use of Fourier series and wavelet transform for obtaining accurate limit cycle parameters. That will give you again accurate critical gain and critical frequency. Those are used in analytical expressions to find the parameters of a transfer function model. Let us go through this simulation study number 1, where we have got a process given by G s is equal to k e to the power minus 2 s upon 4 s minus 1. So, we consider an unstable first order plus dead time process. Now, the process is controlled by the PIPD controller, where the PI controller is in the feed forward path. So, the dynamics of the PI controller is given as now 0.131 plus 1 upon 15.2672 s. Similarly, the unstable process is subjected to an inner feedback controller given by this is your GC1s, this is GC2s, can be written as 0.5 times s plus 1. So, when the unstable process is subjected to a pair of controllers, a feed forward and an inner feedback controller, then it results in satisfactory output. Okay. So, this is the first part of this plot is for normal operation of the system, normal operation of the unstable system or unstable process, of course, with the controllers GC1s and GC2s. Then when the relay auto tuning test is initiated with the relay amplitude of h is equal to plus minus 0.05, we do obtain sustained oscillatory output of this form superimposed upon the set point value or the reference input. Now, so a relay with amplitude 0.05 is connected now. Okay. Once it is connected, then the output takes this form. Now, when the system is subjected to a static load disturbance at 90 seconds, then what happens? What type of output you get? You please see, if this is the 90 second approximately, then we see changes to the sustained oscillatory output, and the sustained oscillatory output for certain duration does not give us symmetrical sustained oscillatory output, or we do not get symmetricity in the output. Okay. But of course, after few cycles, almost after 3 cycles, the normalcy is restored or the sustained oscillatory output becomes symmetrical. Okay. So, for this span of time, we have got asymmetrical output when the relay is symmetrical with the amplitudes plus minus 0.05, whereas after few cycles again symmetrical output is obtained. So, we do get symmetrical output which is exactly of the form that you have got preceding the asymmetrical output. So, this is the symmetrical output you get. So, the effect of static load disturbance is not there after few cycles of the output signal. That means, now with the help of this Pi and Pd controller, this is a Pi controller and this is our Pd controller, we have been able to successfully eliminate the ill effect of static load disturbance during the auto tuning test. And when there is no Pi controller during the auto tuning test, we may get asymmetrical limit cycle output. Please keep in mind, only during the presence of the Pi controller in the loop and when the auto tuning test is carried out, then the limit cycle signal is restored or we do get correct form of limit cycle output. Now, the measurements can be made from the stable limit cycle output. So, this is what I mean by the stable limit cycle output. So, the measurements on the stable limit cycle output will result in correct parameters of the limit cycle output. So, correct values for the peak amplitude and the period of the limit cycle output can be obtained, or the frequency of the limit cycle output can be obtained when the measurements are made from the stable limit cycle output, not from here. So, if you make measurement from this, then you will not only get incorrect peak amplitude, but also you may get incorrect critical frequency or ultimate frequency from the limit cycle output. So, this is very important for us. So, what is this static load disturbance that is given to a process or system during operation? We have got many type of disturbances for a process or system. We have got static and dynamic load disturbances. How static load disturbance is different from that of a dynamic load disturbance? I will give one simple example. Suppose the weight of a bridge. The weight of a bridge and weight of a truck, moving truck, they are different from each other. The weight of a bridge gives us static load, whereas the weight of a moving truck gives us dynamic load. Similarly, a structure, consider one house or so, that also gives us static load disturbance at any point of time, but during earthquake the magnitude of the static load changes and the effective load you get from the structure or building during earthquake is different, and that qualifies as a dynamic load disturbance. So, it is very important to consider the effect of static loads for many systems, because the effects of static loads are there for many practical systems, and effort must be made to nullify the effect of the static load disturbance at the output during the auto tuning test. We shall go to another example or simulation study, where this time the process is assumed to have dynamics G s is equal to 5 b to the power minus 2 s upon s times 1.6 s plus 1. So, thus we are considering an integrating process now. Like the earlier case, the integrating process is subjected to a Pi controller given by G c 1 s h 0.3445 times 1 plus 1 upon 2 s, and a PD controller of course of the transfer function G c 2 s is equal to 0.2094 times 1 plus 2 s. Now, the basic objective of having two controllers are that the integrating processes are difficult to control, and for getting desired output, the inner feedback controller is employed. So, with the help of the inner feedback controller, first the dynamics of open loop integrating process is stabilized, and thereafter the PI controller is applied to get desired response from the system. Now, when the relay is connected, then we do get sustained oscillatory output from the system. So, that sustained oscillatory output will be available with that unit step reference input, or it will basically get superimposed with the unit step reference input. Now, the relay has been connected in parallel with the PI controller. So, this is our PI controller, and the relay has been connected in parallel with the PI controller. As you know, when the relay is connected in parallel with the PI controller, the offset in the output can be nullified, or thus it is possible to get sustained oscillatory output, symmetrical sustained oscillatory output with no effects of static load disturbance. Now, for this for this integrating process, the static load is injected at time t equal to 35 seconds, and let us see the type of waveform we will expect during the auto tuning test. So, when the static load disturbance occurs at 35 seconds, then the output is having asymmetrical output for certain duration. So, this is the duration during which we have got asymmetrical output, and apart from this duration, we do have symmetrical output from the process. So, this is the symmetrical output, and this is the output you get during normal operation of the system, normal operation, of course, with the relay amplitude of plus minus 0.05. So, the relay is symmetrical, we do get symmetrical output when there is no static load disturbance. Now, please do not make measurement for this duration or during this period of the output, and when the measurements are taken, when the limit cycle is stable, then we do get correct parameters of the limit cycle output, and those parameters are nothing but the peak amplitudes and the ultimate frequency or the critical frequency omega u or omega Cr. Now, we will go to one more example, one more simulation study. In this study again we do consider the same process, the same second order integrating process, which dynamics is given by G s is equal to 5 e to the power minus 2 s upon s times 1.6 s plus 1. Now, same P I and P D controllers are used. What is the difference in this simulation study or block diagram we have? Basically, we have injected or added at the output of the process. Please carefully look at this. The output of the process is now corrupted with band limited white noise. So, I have added one more block over here, and this block represents the band limited white noise, band limited white noise. Then we do expect corrupted output from the closed loop system. Now, when the relay is connected, we do get further corrupted output due to the auto tuning test, and the final result will see the type of output you will get will be like this. Okay. So, when there is no relay, you see the type of operation you will get, or the type of output with the band limited white noise, output with the band limited white noise. When the relay is connected in parallel with the PI controller, that times we do get this output without any static load disturbance, but with BLWN. Now, this is also the same output you get, but when the static load disturbance is applied at time 35 seconds, then we obtain this limit cycle output. Okay. Now, what is BLWN? Band limited white noise is normally distributed random numbers. Those can be added to see the effects of, or to realize the effects of sensor noise in a system. And the random numbers with the height of power spectral density of 10 to the power minus 4, that is defined as the noise power. Noise power means power spectral density of the noise with height of 10 to the power minus 4. When this typical noise power is added to the system, then we do get the type of output signal which is quite corrupted with noise. Then how to make measurements for the peak amplitude and the ultimate frequency or the critical frequency accurately? That poses a challenge, because many sensors may not have accuracy. When the sensors are inaccurate or when the measurements are subjected to measurement errors or noise, that time we do get this type of sustained oscillatory output, and it is very difficult to extract correct limit cycle parameters or accurate limit cycle parameters, and unless accurate limit cycle parameters are extracted, then we will get erroneous peak amplitudes and critical frequency, which will result in erroneous ultimate gain and ultimate frequency. Those are used in estimating the transfer function parameters. Thus, the estimated parameters also will be subjected to errors. Now, is there any way we can avoid this? Often it is found that we do get corrupted output signal from many real time systems in spite of many effects employing accurate or reliable sensors. It is not possible to obtain clean output signal, thereby giving us faulty or erroneous model parameters. So, we have to go for some technique which can be used to obtain clean or smooth or denoised signal from that of a corrupted output signal. We shall discuss one such technique known as the Fourier series based curve fitting technique. So, what is there in this Fourier series based curve fitting technique? We will see in details later on. Now, let me discuss about the effects of measurement noise. So, measurement noise is a common problem in almost all process industries, irrespective of presence of accurate sensors. The output is often found to be corrupted. So, that way it is a very common problem in almost all industries. Now, noisy limit cycle output signal makes it difficult to measure its amplitude and frequency accurately. It is essential to measure accurately amplitude and frequency of the limit cycle output or the sustained oscillatory output signal, because based on that only we do have analytical expressions or explicit expressions to find parameters of a dynamic model. So, we have to go for some smoothing technique using Fourier series. And how can you describe a Fourier series? The Fourier series expression for a function y prime t can be given in the form of sum of k equal to 0 to 8 xi 1 k cos k omega t plus sum of k equal to 0 to 8 xi 2 k sin k omega t, where the Fourier coefficients are xi 1 k, k varying from 0 to 8 and xi 2 k, k varying from 0 to 8. Now, when k equal to 0, when k equal to 0, what will happen? Y prime t will be equal to simply your xi 1 k, and k is 0. So, we will get a constant of the form xi 1 0. So, this gives the DC value of the signal y prime t, and rest of the components or terms you will have certain frequency, where the signal is assumed to have a frequency of magnitude omega. So, omega is the fundamental frequency of y dash t. So, it is assumed that we can represent any type of practical system with the help of a Fourier series, and why we have limited our discussion to 8. Ideally, it should be infinite. If you consider more number of terms, then you have got appropriate representation of any practical signal by its equivalent Fourier series. But practically what happens? You have to have computational complexities. To reduce the computational complexities, often it is required to limit the number to certain value, and that is why I have put 8 over here. So, I do consider 7 harmonics, sorry 8 harmonics basically, because I go from k equal to 0 to 8, thereby we have got 9 terms, and that way you have got 8 harmonic components will be considered. What are those harmonic components? Starting with frequency omega, I will get 2 omega like this up to 8 omega. So, that way we will get 8 harmonic components of the signal. So, how can this be used? Basically, the noisy signal will be represented by its equivalent Fourier series representation. So, the noisy signal is suppose like this, then now it is very difficult to obtain correct information about its period or frequency, because at the 0 crossings also you can have noise. So, let me draw this in a more realistic manner. So, I will have noise like this. So, when this is the output signal, sustained oscillatory output signal, then how to obtain the information about its period or fundamental frequency? It is very difficult, because the 0 crossing, I have got hell lot of 0 crossings over here, and so also I have got a number of 0 crossings here. So, how to measure the distance between the two exact 0 crossings? I do not know where the 0 crossings exist. So, that way we may not be able to get accurate information about the ultimate frequency from this signal. Similarly, what about the peak amplitude of this signal? You see which can qualify as the peak. I may get erroneous value if I measure this value. Similarly, I can have multiple peaks. Look at the signal here how many negative peaks you have, this can qualify as one negative peak, this can qualify as one negative peak, this can qualify as, so also this one. So, that way we have got multiple points or multiple measurements, then which one to choose. So, certainly this is going to give us erroneous peak amplitude. That, but when this signal can be represented by a number of signals having multiples of fundamental frequency, then what will happen? I will get one clean signal corresponding to this noisy signal. So, one signal with fundamental frequency must exist, then we will have so many harmonic components. So, if this is the signal with fundamental frequency, that with the higher order frequency, then I will get like this. Is not up to the scale or exact to the scale. Okay. So, you go on getting a number of components now like this. When you add up all these, then you get the practical signal that you have obtained from the system. But the analysis gives us a signal with fundamental frequency. Now, I can make measurements on this signal, and that is a clean signal which can give us accurate values for the peak amplitude, and so also for the instants of zero crossings correctly, from where we can measure the frequency or period of the signal. So, this is the concept, basically the way a curve fitting technique is used to extract a signal with fundamental frequency from a practical signal. Okay. I will consider an example to illustrate that point. So, consider the process with the transfer function of the form G P s is equal to e to the power minus s upon, let us take G s, because we have been taking G s in our studies. So, G s is equal to e to the power minus s upon s plus 1 square. This second order plus date time system or process is now subjected to a relay test with the relay amplitude of h equal to 0.25. So, we are employing a symmetrical relay, and when the relay is switched on at time t equal to 0, then from time t equal to 0 we get some output signal. Then at time t equal to 30 seconds we do apply also a step load disturbance of magnitude 0.5. Now, this plot is not showing the plot from time t equal to 0 to time t equal to 54 seconds. Okay. Why I have neglected that? The main reason for that is that, as I have said earlier, we have to look for the signal that we get after the static load disturbance. So, you look at, we have to collect information from last few cycles of the output signal, okay? Not from the from this period where you have got normal operation, but once you have got static load disturbance, the output gets distorted. So, we have to avoid that. Just prior to stopping the relay auto tuning test, you collect signal, and that signal is of interest, and that is why I have collected the signal from time t equal to 54 seconds to t equal to 70 seconds. So, we have obtained some corrupted signal, and that is shown over here. Now, when a band limited white noise with power 0.0001 is injected, then we get this corrupted output signal. Okay, this is the corrupted or noisy output signal. Now, when the curve fitting is applied, curve fitting is applied now, what we do get? We get the fundamental component of the signal given by the red curve or the plot in red color. So, the red one, if you observe carefully, is the fundamental or the signal with the fundamental component, signal with fundamental frequency. So, the red one, if you look carefully, is no more corrupted and it has got zero crossings, no multiple zero crossings. Unlike the corrupted signal, here it is touching over here and here. So, I have got multiple zero crossings. The red one is not having multiple zero crossings. So, that way you can easily identify the zero crossings. Okay? And using the zero crossings, you can obtain or measure the period of the signal. This is the period of the signal. And now, similarly, if I look at the plot in red, the peak amplitude is unique. Okay. Unlike this plot, which one is to take as the peak amplitude? If you take this one, this might be the contribution from the PSD of the noise, power spectral density or the random values we have added. Okay. So, that way the correct value for the peak amplitude must be obtained from this plot in red. Okay. So, when the Fourier series based curve fitting is employed, then we are able to get the clean waveform or the clean plot, the clean one or the noise free, I would say noise free one or the denoised one with the help of the Fourier series analysis. Now, what has been done? How we have obtained 3 cycles of the noisy output signal is plotted over here. If you see, almost 3 cycles of noisy output signal is plotted. Along with that, the recovered signal obtained from curve fitting is also provided. How do you recover this one? It is all about simply data fitting. So, given a set of data, you try to fit it with the expression we have obtained for the curve fitting. So, this is the data available. Left hand side we have a set of data. That means, what are available? y1 prime, y2 prime, y3 prime and so on, and we have got another data set of y1 prime prime. So, corresponding to the time. So, I will write t1, t2, t3. So, at different time instants you have got different data, and when you collect the data set t and y and fit with that of the actual signal y prime t, then you do get various coefficients, Fourier coefficients. So, when a corrupted signal y t is fitted with the Fourier series given in the right side of this expression with the terms y t is equal to a 0 plus sum of I equal to 1 to 4, a I cos I omega t plus sum of I equal to 1 to 4, b I sin I omega t, then we get different coefficients like a1, a2, a3 and a4, and similarly b1, b2, b3 and b4. Of course, the DC value of the signal is given by the coefficient A0. So, we will get these estimated values for these coefficients with certain confidence levels or bounds, those are given over here. Now, please keep in mind this output data is collected and fitted with a Fourier series which has got 9 number of coefficients. Keep in mind, I have limited my simulation or program to up to 4. That means, how many harmonic components we will have? We will have 4 harmonic components for the corrupted signal. So, the corrupted signal is being mapped with that of a signal with fundamental frequency, and then you have got harmonics, different harmonics. So, we have got 3 harmonics additionally, okay, apart from the fundamental frequency. So, basically the signal is represented by a signal which has got 4 frequency components. Then we get the ultimate frequency from the mapping H. Omega u is equal to 1.36, one digit is missing here, 1.368. So, thus the ultimate frequency is estimated as 1.368, and from the clean signal, from the fundamental component of the signal, we get the peak measured as AP is equal to 0.177. Had there been no noise added to the system, we do get the peak H AP is equal to 0.179 and the ultimate frequency as 1.368. That shows that using this Fourier series based curve fitting, it is possible to obtain correct information of the signal, correct limit cycle parameters from the corrupted signal, okay? Because the critical frequency or the ultimate frequency is obtained accurately and there is minor error in the peak amplitude, okay? Next, we shall go to some other technique that is known as wavelet based identification technique. So, why we are not happy with this technique, or what are the limitations of this technique? Actually, if you see the tabular values, the percentage error in estimation of the peak amplitude is almost minus 1.12 percentage, and percentage error in estimation of the ultimate frequency is almost 0, okay, is 0. So, still the method is subjected to some estimation error. Although we do obtain denoised or clean signal using Fourier series based curve fitting, still the method is not free from errors. Therefore, effort is made to discuss another technique known as wavelet based identification technique that can be used to obtain or estimate the parameters associated with a noisy limit cycle accurately. Now, I will introduce some Gaussian function, some smoothing Gaussian function with non-zero DC value and a scale of A h theta a t is equal to 1 upon square root of A theta t upon A. When you take the plot of this function, then you can see the way it appears. Now, what is theta? Theta is not time delay in this case, this is a function. Okay. Now, theta is the basis function of a wavelet, and A is the scale that controls dilation of the signal. Okay. So, I do believe that you have some basics of wavelet transforms and wavelets. So, this smoothing function can be used in our study. Now, when this wavelet transform of this function, smoothing Gaussian function is found. So, wavelet transform of the noisy signal can be now given as W f A alpha. W f wavelet transform is now a function of the scale and some shift parameter. Alpha is a shift parameter. Then the wavelet transform can be given by the expression W f A alpha is equal to minus A times first order differentiation with respect to the shift parameter of inner product of the function and the basis function. The function means what? The signal, the corrupted signal with that of the basis function. Okay. So, the inner product of the two functions, what are the two functions? The signal shown by the function f t and the basis function given by theta a in our case. So, the inner products of the two and first order differentiation is taken. That results in interestingly a situation where at local extremum of the signal, the wavelet transform will result in coefficients with 0. Okay. So, coefficients with values 0. What I mean by that? Suppose the signal is original signal is corrupted like this. When its wavelet transform is found, this is the signal f t upon t versus t, then for the wavelet transform W f A and alpha will give us samples, where the samples will have 0 magnitude at the extremums. Where are the extremums of the signal? We do have extremum here, we do have extremums here. So, at the exact extremum only due to the effect of basis function, we will get the coefficient as 0, and at any other location, suppose this is the correct extremum, then I will have a wavelet transform with coefficient 0. So, how this we have got two extremums now. What about the remaining coefficients? Those will be non-zero. So, I do not mind what are these values, what these values you have. So, I can have a plot like this, only at the extremum here, another extremum is here suppose, then you will have 0. So, actually the form or nature of this wavelet transform plot is not important. What is very important for us is that the extremum of the signal is tracked accurately by the wavelet transform technique. So, using the wavelet transform, the peaks associated with the peaks of the corrupted signal can accurately be found. How can you find? As I have done here. So, the peaks result in 0 values, therefore, we can accurately find the 0 crossings. So, what is the benefit of getting the 0 crossings? We know that the 0 crossing of this wavelet transform corresponds to the peak of the corrupted signal, means actual signal that is present in the corrupted signal. Okay. So, if the actual signal, let me again give this example, suppose this is the actual signal or the real signal or uncorrupted signal. Now, it will be corrupted like this. Okay. Then the wavelet transform of this one, this is the peak from the clean signal and this is the peak from the clean signal. So, the wavelet transform will be having some value like this. So, you will have a plot like this. So, the peaks have been located correctly. So, from the location of the peaks, basically we do get correct information about the zero crossings of the signal, and from the zero crossings you do get correct information about the period of the signal or ultimately the ultimate frequency of the signal. Okay. So, omega u can be obtained accurately. Okay. That is very important. What other information you can obtain? Now, you have been able to locate where your peak remains, then take the averaging of this signal. So, find the average of this signal around that peak, then you can locate or you can find correct information about the peak amplitude. Okay. So, the averaging, first of all it is very important to locate, the zero crossings. Okay. Sorry, this is the zero crossings, and next is it is very important to locate where your actual peak amplitude remains. So, once you have located, if the noisy signal is averaged around that, then the correct information about or correct measurement of peak amplitude can be obtained or can be made. So, that is the benefit you get from wavelet based identification technique. Let us see some example. For the first order plus dead time transfer function model, a relay with edge equal to 1, parameter 1 produces a sustained symmetrical process output as shown over here. When the process output is corrupted by the noise with variance of 0.0025, which gives a signal to noise ratio of 4 approximately, I get the signal corrupted with this much of SNR in this form. So, basically this signal has resulted in this one. Then how to get back this signal from the noisy one? That is what we have been discussing. So, given a noisy signal like this, how to retrieve the correct limit cycle output signal. Okay. Now, when the wavelet transform of this is taken, what type of output we get? This is what we get. So, if you look at this, then the peak of the output signal are here. Okay. So, basically the peak of the peak corresponding to these peaks will have these zero crossings. So, the period can be measured easily, because the period is nothing but if you measure from any peak to peak, you do get information about the period of the signal. Okay. And from the period you can get correct information about the ultimate frequency. Okay. Now, how to find the magnitude? Now, once I have located where the peaks remain, suppose at this time the peak remains, then I will take the average of this signal around that and I will get correct information about the peak amplitude. Thus, it is possible to obtain or retrieve the signal from the corrupted or noisy signal. Okay. Then the noise reduction technique is used to measure the values A p of this and of peak amplitude of this from the shown data, and then the describing function method is employed to estimate process model parameters. So, when you see this one, the process model parameters now calculated from this noise free or recovered signal have got estimation or errors of 0.0004% for the time delay and about 18.41% for the time constant. So, these are the underestimated values. Okay. So, this way although it is also not free from errors, keep in mind, but the wavelet transform provides us some cleaner signal which can be used for measurement of limit cycle parameters. So, in summary, we have noisy limit cycle output signal makes it difficult to measure its amplitude and frequency necessary for estimating parameters of a transfer function model. Now, Fourier series based curve fitting can be used to obtain smooth signal and thereby obtain critical parameters of the limit cycle output signal effectively. Now, also wavelet transform can be used to measure accurately critical parameters of the limit cycle output signal. So, thus we have studied two techniques using which we can retrieve limit cycle output signal from the noisy one. Now, any point to ponder? Do we have any other technique for improved identification in the face of measurement noise or when the limit cycle output is corrupted with noise? Apart from the wavelet based smoothing technique or curve fitting technique or and the Fourier series based denoising technique or curve fitting technique, we do have dynamic noise reduction methodologies and active filters. Those can be used to improve upon the identifications or to make correct measurements from noisy signals. Thanks.